Mars is the only planet in the solar system whose surface you can look at in detail from an armchair. Venus is under cloud. Mercury sits in the glare of the sun. The giants have no surface to look at. Mars has weather, seasons, ice, dust, mountains, and dry riverbeds. And it has been photographed from orbit and from the ground for 60 years. Tonight, we are going to spend the whole time on it. 14 things, all of them measured, starting with the color and ending with the one thing about it that is genuinely unresolved. A great deal of what people know about Mars comes from films, and films have been unkind to it. The storms cannot knock anybody over. The sky is not red. The sunsets are the opposite color to ours. We will get all of that straight as we go. Nothing here needs to be remembered. There is no argument to follow. If you are here to fall asleep, that is a perfectly good way to listen. Mars is not red. It is the color of butterscotch. Seen from Earth with the naked eye, Mars is a steady orange point, and every old civilization that wrote anything down noticed it and connected it with blood or with war. Stand on it, and the color is gentler than that. The ground is a dull tan, the shade of butterscotch or weak tea with milk. Photographs from the surface that have been carefully color-corrected show a landscape that would look ordinary in a desert on this planet. The color comes from a very thin coating. The dust that covers almost everything contains iron oxide, which is rust, in grains finer than talcum powder. It is a few micrometers thick in places, and it is everywhere because the wind has been sorting it for billions of years. Underneath, the rock is dark gray basalt. Where a rover wheel scrapes the surface, or where the wind has swept a slope clean, the planet is the color of a cold beach in the north. We are confident about this because every rover carries a calibration target, a small plate of known colors bolted to the deck, photographed alongside the landscape. It exists purely so that the colors in the pictures can be checked against something certain. The sunsets, they are blue. On Earth, the sky is blue and the sunset is red. On Mars, it is the other way round, and the reason is the same physics working on different material. Our air is clear, and the molecules in it scatter short blue wavelengths in all directions, which paints the whole sky blue. At sunset, the light comes in through much more air. The blue is scattered away, and what is left is red. Martian air is thin, but it is loaded with those fine dust grains. Grains that size scatter red light strongly and sideways, so the daytime sky is a pale butterscotch color all over. Blue light passes through the dust more directly instead of bouncing away. So near the setting sun, where you are looking straight down the beam, the light that survives is the blue. A cool blue glow spreads around the sun for a diameter of several times its width, and it lingers because dust stays suspended a long time in weak gravity. There are images of this taken from the ground, and they are among the strangest pictures in the archive precisely because they look so calm. A small white sun setting into a hazy tan desert with a patch of cold blue around it. A day on Mars is only 40 minutes longer than ours. Of all the coincidences in the solar system, this is the one that makes Mars feel closest. Mars turns once in 24 hours, 39 minutes, and 35 seconds. That period is called the sol. Its axis is tilted by about 25 degrees, which is within a degree or two of ours, so it has the same 4 seasons for the same reason. The differences are in the length of things. The year is 687 Earth days, so each season is roughly twice as long. The orbit is noticeably out of round, which makes southern summers shorter and hotter, and northern ones longer and milder. There is a practical consequence that people who work on Mars missions know well. A rover team on Earth that wants to work while its rover is in daylight has to shift its own working day 40 minutes later every day. After a few weeks, they are arriving at the office at 3 in the morning. Teams did this for months on end during the early rover missions, with watches specially built to run slow. We know the rotation to a fraction of a second by tracking fixed features, and by radio ranging to the landers, which have been sitting still on the surface for decades. There is as much ground on Mars as there is dry land on Earth. Mars is small. The radius is about 3,500 kilometers, roughly half of ours, and the surface area works out at about a quarter of the Earth's. But the Earth is mostly ocean. Only about 3/10 of our surface is dry land, and when you compare the dry parts, the two numbers come out almost the same. About 145 million square kilometers each, near enough that the difference depends on where you decide a coastline is. That is worth sitting with for a moment. Every desert, every mountain range, every forest and city and field on this planet, laid flat, would cover Mars with very little left over. The gravity there is about 38% of ours. A person who weighs 80 kilograms here would weigh 30. That lower gravity is part of why the landscape got so large. Mountains and canyons can stand taller before their own weight brings them down. The figures come from radar and laser altimetry from orbit. One instrument in the late 1990s fired a laser at the surface 600 million times and built a map of the whole planet, accurate to a few meters in height. A dust storm on Mars could not knock you over. This is the thing films get most wrong, and the correction is simple arithmetic. The air pressure at the surface of Mars is about 6 millibars. Ours is 1,000. So the atmosphere there is well under 1% as dense as the air in the room you are in. The push a wind gives you depends on the density of what is moving as well as its speed. A Martian wind at 100 kilometers an hour carries roughly the force of a gentle breeze here, about the pressure you feel from a fan across a room. It would not knock over a person, or a lamp, or an empty box. What it does do is lift dust, because the grains are so fine and the gravity so weak. Once lifted, dust stays up for weeks. Every few Martian years, a storm grows until it covers the entire planet, and the surface is hidden from orbit for months. Sunlight at the ground drops to a fraction of normal, and solar-powered machines have been lost to that darkness. So the danger is real, and it is not force. It is dust in the air, dust on the panels, dust in every hinge and seal, and dust that does not settle for a very long time. A quarter of the air freezes onto the poles every winter. The Martian atmosphere is almost entirely carbon dioxide, and at the winter pole, it gets cold enough for carbon dioxide to freeze straight out of the air onto the ground, about minus 125 degrees. So each winter, a cap of dry ice a meter or two thick builds up over the pole. The gas that forms it comes out of the atmosphere everywhere on the planet, and the air pressure across the whole of Mars falls measurably as it does. Then that pole tilts back towards the sun, the ice turns straight back into gas without melting, and the pressure rises again. The swing is around a quarter of the total atmosphere, moving from air to ground and back, twice a year. Nothing like this happens here. Our seasons move water around. Mars moves its own sky. We know it because two landers in the 1970s carried simple barometers and sat in place for years, recording the pressure, day after day. The graph is a clean seasonal wave, and it has been confirmed by every lander since, most recently by an instrument sensitive enough to feel the pressure change from a passing dust devil. Water cannot stay liquid on the surface. Put a glass of water on Mars, and it does not simply freeze, and it does not simply boil. It does both at once, and then it is gone. Water needs pressure to stay liquid. Below a certain pressure, there is no temperature at all where liquid water is stable. It goes straight from ice to vapor, the way dry ice does here. That threshold is about 6 millibars, and the Martian surface pressure sits right at it, wandering above and below with season and altitude. At the bottom of the deepest basins, the pressure is high enough for liquid water to exist for a short while if the temperature also happens to be right, which is rare. Almost everywhere else on the planet it cannot. Salt changes the arithmetic because very salty water stays liquid at lower temperatures. For some years, the dark streaks that appear on warm slopes in summer were taken as brine seeping out. The evidence has moved. Most work now favors dry sand and dust sliding, and the question is not fully settled either way. It is an honest, open case, and it is worth knowing that the first exciting explanation is not the one currently in front. There is enough buried ice to wrap the planet. The polar caps are the obvious ice. Under the seasonal dry ice, the northern cap is water ice, roughly 1,000 kilometers across and up to 2 kilometers thick, layered like a stack of paper with dust between the sheets. The unobvious ice is everywhere else. Radar instruments in orbit send pulses into the ground and listen for the echo. And across the middle latitudes, they keep finding sheets and lobes of nearly pure water ice buried under a meter or two of dust. Some of them are the size of small countries. A few are plainly glaciers, with the shape of glaciers, sitting in valleys with rubble pushed up in front of them. If all the known ice were melted and spread evenly over the planet, it would make a layer somewhere in the range of tens of meters deep. Estimates vary quite widely depending on what is counted and how deep the radar is trusted, so that is the honest form of the number rather than a single figure. What is not in doubt is the state of it. The water on Mars did not all leave. Most of what stayed is frozen, and most of the frozen part is out of sight. There is a river delta with a machine standing in it. From orbit, one of the clearest things on Mars is a fan of layered sediment spread out inside a crater rim, exactly the shape a river makes where it slows down and drops what it is carrying. It is not the only one. There are valley networks that branch like drainage systems, channels cut by enormous floods, and lake beds with shorelines at matching heights. Clay minerals show up in the spectra from orbit, and clays form in standing water over long periods. Since 2021, a rover has been driving on one of those deltas. It has photographed cross-bedding in the rock, the diagonal layering left by moving water, and rounded pebbles that were tumbled along a bed. It has drilled and sealed samples of that rock and left them in tubes on the ground for a future mission to collect. The dates come from counting craters and from the chemistry, and they point to roughly 3.5 to 4 billion years ago. So Mars had rivers and lakes for a long stretch early and then lost them. The next fact is the best answer we have for why. The air left when the magnetism stopped. Mars has no global magnetic field now. It had one once, and the evidence is written into the oldest rocks in the southern highlands, which are magnetized in broad stripes, the way rock is when it cools in a field. A magnetic field is made by molten metal circulating in a core. Mars is about half the diameter of Earth, so it holds heat far less well, and its core stopped circulating early. Best estimates put the end of the Martian dynamo at around 4 billion years ago, not long after the planet formed. Without the field, the solar wind reaches the top of the atmosphere directly. It strips gas away, ion by ion, and the lighter the gas, the easier it goes. That process is not a theory. A spacecraft has been in orbit since 2014, measuring exactly this, watching escaping ions leave the planet, and watching the rate rise sharply during solar storms. The measured loss rate, run backwards over billions of years, roughly accounts for the missing air, so the water did not evaporate away for no reason. The planet lost its shield first, then its air, and then the pressure needed to keep water on its surface. Sound travels at 2 different speeds on Mars. Until recently, nobody had heard Mars. Several missions carried microphones, and none returned usable sound. In 2021, a rover landed with 2, and they worked. The recordings are quiet. Wind, the whir of the machine's own arm, the tapping of a laser on rock. Sound is faint there because the air is thin, and it does not travel far. Then the analysis turned up something nobody had planned for. In carbon dioxide at that low pressure, high-pitched sound travels faster than low-pitched sound. The measured difference is about 10 meters per second, in a medium where sound moves at around 240 in total, compared with 340 here. The practical effect is strange to imagine. If 2 people stood a distance apart and one spoke, the high parts of the voice would arrive slightly before the low parts. Over 100 meters the gap would be noticeable. A conversation across open ground would not simply be faint. It would arrive out of order. Nowhere on Earth does this happen at any pressure people live in. It was predicted from theory beforehand, and then measured, which is the best way for anything on a list like this to arrive. One of its moons is falling. Mars has 2 moons and neither is round. Both are small, dark, cratered, and shaped like potatoes, and both would be unremarkable asteroids if they were anywhere else. Phobos, the larger, is about 22 kilometers across and orbits closer to its planet than any other moon in the solar system, about 6,000 kilometers above the ground. It goes round in 7 hours and 39 minutes, which is faster than Mars turns. From the surface, it rises in the west and sets in the east twice in a single day. It is also getting closer by roughly 2 centimeters a year, dragged down by tides. That is slow, and the end is not. In something like 30 to 50 million years, it comes inside the distance, where the planet's pull is stronger than the rock's own strength. It will break apart, and Mars will most likely have a ring for a while, and then a line of debris will come down. Deimos, the smaller one, is doing the opposite and drifting slowly outwards. Where they came from is not settled. They look like captured asteroids and are made of similar material, but their near-circular orbits are hard to get by capture. The other idea is that they formed from debris after a large impact. A sample return mission is on the way to settle it. You can hold a piece of Mars in your hand. There are somewhere over 300 rocks in the world's collections that came from Mars, and a few of them can be bought. The route is straightforward. A large impact on Mars throws material off the planet fast enough to escape its gravity. Some of that drifts for a few million years and eventually lands here. Most is found in Antarctica or in deserts, where a dark stone on pale ground stands out. Knowing they are Martian is the good part. Some of these rocks, contained tiny pockets of gas trapped in glass that melted during the impact. When that gas was analyzed, its mixture of nitrogen, argon, and carbon dioxide matched the Martian atmosphere as measured directly by landers in the 1970s. Not approximately, isotope by isotope. That is a rare thing in science, a fingerprint taken on one planet matching a sample sitting in a laboratory drawer on another. One of these meteorites was announced in 1996 as containing possible traces of ancient microbial life. That claim has not held up. Most researchers now think the structures can form without life, and the finding is not accepted, though the paper it prompted did more than anything else to restart Mars exploration. Nobody agrees about the methane. Every list like this should end honestly, so here's the thing about Mars that is not settled. Methane is a simple gas, and on Mars it should not last. Sunlight breaks it apart within a few hundred years, which is nothing. So any methane in that air was put there recently, geologically speaking, by something. A rover on the surface has been measuring it since 2012. It finds a small background amount, well under 1 part per billion, that rises and falls with the seasons, and occasional spikes 10 times higher that come and go within days. An orbiter built specifically to hunt for trace gases, with instruments far more sensitive, has looked for the same methane from above and found nothing at all, below its detection limit, over years of observation. Both instruments are good, both teams are careful. The proposed explanations include gas seeping from the ground and being destroyed near the surface before it can rise, and something about the measurement itself that is not yet understood. Methane can be made by rock and water reacting, with no biology involved at all, and that is the leading explanation if it is real. But the honest position today is that we do not know whether there is methane on Mars. That is 14 of them. There is a thread through this episode worth saying before you go. Everything here was learned by machines that had to wait. A radio signal takes between 4 and 24 minutes to reach Mars, depending on where the two planets are. Nothing can be driven in real time. A rover is given a day's instructions in the morning and reports back in the evening, and if it went wrong hours ago. Every 2 years or so, the sun passes between the planets and controllers stop sending anything at all for a couple of weeks, because the signal cannot be trusted through the glare. The machines park and wait it out on their own. The barometer that found the seasonal pressure wave ran for years. The orbiter watching air escape has been at it for over a decade. The rover in the Delta is leaving tubes on the ground for a mission that has not launched. Mars is out there tonight, turning once every 24 hours and 39 minutes, with a blue glow around the setting sun and a quarter of its sky waiting to fall as snow. Sleep well.